Okay, so we are continuing with the tutorial questions for the uh, Materials and Manufacturing Engineering A. And now we are going to go to the week number 5 tutorial, which was mainly about the orthogonal cutting operations. So in this slide that we have in the module, you can find that we have multiple examples, but mainly going to be about what the process of the orthogonal cutting, where you can find its video available for you on the canvas within the same module. And also you can go back to my YouTube channel and you're going to find more details about the operation. Also, you will find some examples that I put for the milling operation to calculate the rate of the material removal, or the turning operation to calculate the time of the machining. And from there, well, I can give you some help with that during the Q&A session we're going to hold on Tuesday. So let's go first and take a look about the example we have here. For the first example, we need to calculate what we call the chip ratio, R. Find the value of the phi, which is the orthogonal face angle, plane angle, sorry, and we need to calculate the gamma, which is shear strain. I'm going to just go through the equation we have here. So the helpful equation is the chip thickness ratio is the original thickness over the final thickness, and this value should be less than 1. Okay, less than 1, you have to remember that. And then you can find the equation to find the value for the phi. So the tangent of the phi, or what we call the shear plane angle, is equal to the R ratio multiplied by the cosine of the alpha, which is the rake angle, divided by the 1 minus the R multiplied by the sin of alpha. Continue with that, find the value for the gamma, which is the shear strain value, strain unitless. Okay, so the gamma is going to be equal to the tangent of the phi minus the alpha. Phi is the shear plane angle minus the alpha, which is rake angle, plus the cotangent of the phi. The cotangent is 1 over tangent, or 1 over the value we got from the equation 21.3. Now, more calculation about the shear force cutting, and first about the friction angle. Okay, so the friction plane angle is going to be equal to the tangent inverse of the coefficient of friction. And that's what we can get from the equation 21.6. Now, continue with that. The value for the shear stress is equal to the shear force by the area of the shear. And the area of the shear is going to be equal to the thickness of the chip before the cut, multiplied by the width, multiplied by the sin of phi. The other equation we can have for the friction force, for the normal force on the friction force, for the shear force and the force normal to the shear force, can be found from the equation 21.9 to 21.12, where the FC and the FT are the cutting force and the thrust force. These are something can be measured, and we mentioned that during the lecture slide. And here we have something about what we call the merchant equation. This is merchant equation. So in merchant equation, the phi is shear plane angle 45 plus alpha divided by 2 minus beta divided by 2. The higher the phi is, the lower energy for the cutting we are going to use. So to get the best value for the phi, highest value for the phi, we need to reduce the value for the beta and increase the value for the alpha. Okay, now here about the cutting power, and specific energy also can be calculated by using the equation 21.17 up to the 21.21. I think that we don't have too many questions related to that, but anyway, it's going to be nice to go through that. The temperature difference during the cutting operation due to the friction can be calculated by using what we call the Cook equation, that equation. And temperature difference is going to be equal to 0.4 multiplied by the U, which is the specific energy, divided by the rho C, okay, which is given here as the value for the volumetric specific heat of the work material, which is a constant value, multiplied by the velocity TO divided by the K up to 4.33. So you can actually write down these parameters in your notebook, and you can use it to do the calculation if you have this question. However, let's go through an example on how to calculate all these parameters, and again to play my PowerPoint now to go through the steps. So in this example, and we're going to highlight the parameters given to us, we start with first. Okay, so we have machining operation that approximates the orthogonal cutting, and the cutting tools has a rake angle. So here first we had the rake angle of 10 degrees, so that's the alpha. The chip thickness before the cut, TO, is 0.5 millimeters, and the chip thickness after the cut, TC, is 1.125 millimeters. Chip ratio should be less than 1, so it's going to be TO over the TC. During the cutting force, that's the FC, and the thrust force, which is the FT, are to be measured during the orthogonal cutting operation to be the FC is 1,559 Newton, and the FT is 1,271 Newton. The width of the orthogonal cutting operation, W, is equal to 3 millimeters. In addition, the volumetric specific heat of the work materials, rho C, is equal to 3 multiplied by 10 up to the power minus 3 joule per cubic meter degree. And the thermal diffusivity is given as 50 multiplied by 10 up to the power 6 meters squared per second, or 50 millimeters squared per second. That's represent the value for the K we can have in the Cook equation. So let's see what's required in this question. The shear plane angle and the shear strength, phi, and the gamma. The shear strength of the work material, shear strength, the tau S. And we need to find the friction angle, beta. And we need to find the coefficient of friction, mu. Cutting power and specific energy. If the cutting speed is going to be 100 meters per minute, so that's the V. And we need to find the value for the cutting power and the value for the specific energy U. And then the delta T. So let's start to do the operation one by one. I think that the easiest one is going to be the phi. So the thermal diffusivity is the ratio of the heat conductivity rate of the materials compared to the heat storage capacity. Let's go with the units to remember. Actually, I just put this one here. Don't worry about that. Let's do it through the calculation. Start first with finding the value for the R. So we said that the initial thickness was 0.5 and the final thickness was 1.125. And then we can simply put that in the equation, and we'll get the value for the R to be 0.444. If this value less more than 1, that you are in the wrong direction. Okay. Now we calculate the value for the phi. So remember, the equation for the shear plane angle is given by the equation of the tangent of the phi is equal to the R cosine of the alpha divided by 1 minus the R sin of the alpha. Now we put the parameters in. We know the alpha is 10 degrees, the R is 0.44. Calculate that. We can find that the value of the tangent is 0.4738. So that means that the phi is equal to 25.4 degrees. Now we continue with that again to calculate the shear strain value. Tangent of the phi minus the alpha plus the cotangent of the phi. So the phi is 25.4, the alpha is 10, the value is going to be 2.386. So this is shear strain. We don't have a unit for that. Strain, no unit. Now once again, if you would like to build that in your calculator, Excel calculator, you have to remember only one thing, that in the Excel, if you don't want to have a big headache to make the changes, you can simply calculate everything in radian, and then you have to put it back to a degree. And I think that you know how to change from degree to radian, radian to degree. If you change from degree to radian, you divide by 180 and you multiply by pi. and vice versa is going to be the same thing if you want to change from the other way. Now we go to the next step. Now we need to calculate the shear stress. To calculate the shear strength, we need to calculate first the area of the shear, or the AS. So the TO, which is the initial thickness of the chip, which is 0.5, multiplied by the value of W, which was 3 millimeters, divided by the sine of phi, which is the sine of 25.4. So this will give me the area to be 3.497 millimeters square. Now I can use that to calculate the shear force by using one of the equations from the 2112 to 2117, I don't remember. Anyway, so the shear plane area, the shear force is given by the equation of the Fs is equal to the Fc cosine of the alpha minus the Ft sine of the phi. Now we have these two values measured already, the Fc and the Ft. And we know the alpha and we know the phi, so we can simply put that in the equation, and we will get that the shear force is equal to 863 Newton. Now we know the area, we know the force, just divide them. And we can find the shear strength value to be equal to 247 Newton over millimeter square, or is going to be 247 megapascal. That's it, we found the value for the shear strength. Okay, now once again, we can put all that in the calculator. Changing the parameter will give you the answer. Remember that there will be some possibility that we can change the equation, so I can give you the value for the, where's my pen? I can give you the value for the tau s. Then you can go back to find the value for the, for example, I give you the AS, so you can find the value for the FS, right? You can do that. Or I can give you the Fs and you can find the value for the AS, and you can go back to find the value for the width of the chip. We have many possibilities that do the same thing. The only thing you need to do is just write down the equations on a sheet. Then when you get to the question, you can simply rearrange the equation as you can. Remember that most of the question will be given to you again to contain their equations. Now we need to find the value for the coefficient of friction and the friction angle. So we use the Merchant equation. In the Merchant equation, now we know this one is 25.4. This is 10 degrees, so I can calculate the value for the beta. So I can rearrange the equation to have that the beta is equal to 2 multiplied by 45 plus alpha divided by 2 minus pi. Put the parameters in, and we will get that the value for the beta is equal to 49.2. The coefficient of friction is the tangent of this angle, and this will give me that the value is as 1.16. That's quite high. But anyway, it's cutting tool do a friction with the chip. So we consider that this acceptable value. Now we continue with that, calculating the power. Now we remember that we know the cutting force and we know the velocity. One thing to remember, to calculate the power in watt, I need to change the velocity to be in meter per second, okay, and the force to be in Newton. So here what we've done, actually I'm going to multiply it directly. We're going to have Newton meter per minute, then I'm going to change it to Newton meter per second, and this will be 2,598 watt. Now let's calculate the specific energy. So specific energy is by using the power of the cutting divided by the rate of the material removal. So the rate of the material removal, okay, to find that, we can use the equation of U, that the cutting force multiplied by the velocity of the cutting divided by the velocity of the cutting multiplied by the TO multiplied by the W. Okay, so the cutting force divided by the chip thickness at the cutting multiplied by the width. Or we can just simply use that. Okay, so I'm going to end up that the specific energy is going to be equal to 1.039 joule per cubic millimeters. Now, the last thing I think is going to be the finding the temperature. So the cutting speed must be converted to millimeter per second because U and the rho C given to us in millimeter units. Thus, the velocity is going to be equal to 1,667 millimeter per second. Now let's put everything in the equation, the Cook equation. So now we know the U, we know the rho C, we know the K, we know the TO, we know the velocity, put everything in, and get the answer of 353 degrees. Remember something, if you're not going to try to calculate this value with your calculator, you're not going to get the correct answer. So I'm going to actually show you some steps on how to do the calculation. But just one thing, we have a hint here. Okay, so that's how we use the value for the rho C. So I'm going to bring my calculator and let's try to do some step-by-step calculation for this value. So if I was you and I'm going to have similar equation, I will do the following. First, I'm going to calculate this value, take it to the power of 0.33. I'm not a big fan of using the calculator to make one equation with all the parameters and press equal to. This is usually going to give you mistakes. So I will start with 1,667 multiplied by 0.5 equal to, divided by 50 equal to. Now this value, I will take it to the power of 0.333. So up to power 0.333 equal to. Now the 2.552, I will multiply that by 0.4. I will multiply that by 1.039 equal to. Now I will divide this value by, open the bracket, and I will put the 3 times 0.001. Okay, so we're going to have 353.55. That's it. That's as simple as we can. Once again, do the sequence for the calculation. You can see I just did it without any preparation, but I got the correct answer, as long as you do it wisely without trying to jump to a fast answer. Okay, thank you very much. I'm going to come with you later with the calculations for the welding operation.